All right, we're going to discuss Chapter 22, Reflection and Refraction of Light. Let's discuss the cover cover image. They show a little white cup with a pencil in it, and you've seen similar things. If you've gone to a restaurant and they serve you a glass of water in a clear glass with a straw in it, it looks like the straw is bent. This is a result of the speed of light having different values in water where it's slower, and the accepted value of the speed of light 3 times 10 to the 8 meters per second in air. And so that's why we have this image. That's why you see that it looks like a straw is bent in a glass of water, and you see it in other effects in swimming pools and whenever you have light going through different media, you'll see this refraction effect. And here's a good example. They have this very fine beam coming in at an angle of incidence at 60 degrees, and you can see the reflected angle is at 60 degrees also. So this is the angle of incidence, this is the angle of reflection, and you can see that they're equal, and that's one thing that we'll learn. Theta equals theta prime, where theta is the angle of incidence and theta prime is the angle of reflection. But you also have, you can see how the light doesn't come straight through to 60 on this side. It's going through glass, and it's got an angle that what we call the angle of refraction is this angle here. It's about, looks like it's about maybe 34 degrees. And we'll learn how to calculate or predict what these angles are based on the index of refraction of the material. But we're getting a little ahead of ourselves. First, we're going to discuss the nature of light. And Newton taught, and everybody believed that light was just particles that were coming from the sun or a candle or wherever they were coming from. It was just particles of light coming, and some believe, like Christian Huygens, he proposed that it was waves, and people didn't believe that it was waves for several reasons. One, when you discuss waves, you need a medium. You have waves on a guitar string, waves in water, sound waves in air. You need something to disturb. Well, the light was reaching us from the sun with no apparent medium. How could it be waves? And so people questioned that theory. But in 1801, Thomas Young showed that light exhibits interference patterns if you put the light path through two slits. And it's like, well, if they're particles of light, you're not going to have these interference patterns. So he showed that it was indeed it was a wave. In 1865, Maxwell predicted that light was a form of higher frequency electromagnetic wave, and he even predicted that the speed would be 3 times 10 to the 8 meters per second. And then in the late 19th century, Hertz discovered the photoelectric effect, where that a clean metal surface would emit charges when exposed to ultraviolet light. No light, no charges would be emitted, but you put light on and the charges are emitted. What would cause this? And it was Einstein that published a paper that formulated the theory of light quanta, particles of light, to explain the photoelectric effect. So here we've got two different effects, and which one is right? Well, first of all, before we get there, Einstein showed that the energy is equal to hf, where f is the frequency of the light and h is Planck's constant, 6.63 times 10 to the minus 34 joules per second. And we'll learn that there's a dual nature of light. In some experiments, light acts as a wave, and in others, it acts as a particle. So there's this dual nature of light. It can act as a particle, but it can also act as waves. And We'll discuss this a little bit more when we go to in the next sections.